Good morning, good afternoon, good evening, class. This is Mr. Arocena, and on today's video, we're going to be talking about how to determine the strength of acids and bases that are not strong acids or strong bases. Strong acids and strong bases are really easy to identify because in your table of acid and base strengths, there were 6 strong acids, and if you remember what they were, see if I remember what they were. These are your 6 strong acids. So that's hydrochloric acid, perchloric acid is HClO4, hydrobromic acid, hydroiodic acid, sulfuric acid, and the last one was nitric acid. There we go. So these are your strong acids. So those acids are all strong. But then there's a whole pile of other acids which we called weak acids. And weak acids have a varying strength. And we're going to discuss how to determine the strength of these weak acids relative to other weak acids. All right. So the strength of the acid or base really refers to how it is able to give up or absorb hydrogen ions. So strong acids, we know, give up all of their hydrogen ions, except for sulfuric acid, which actually only gives up 1 hydrogen ion, and then it becomes bisulfuric acid, I think. But anyways, yeah, so strong acids have a great ability to do that, other acids and lower ability to do that. Now, the way we can sort of tell is based on the Ka of the acid. So if you remember, our generic acid equation was we had an acid, we would add that to water, and then it would create hydronium, and then a corresponding conjugate base. And this would always be in some kind of equilibrium. So Ka refers to how where the equilibrium is sort of shifting towards. So if Ka is higher, it's shifting the equilibrium more towards the product side. And that means then that if you have a high Ka, you have a higher ability to create the hydronium ions. Or another way to put it, you have a higher ability to give up your hydrogen ions to create hydronium when combined with water. Lower Ka means that this forward reaction is not as favored. Okay. Stronger bases are kind of the opposite in that they are better able to absorb H+ ions. So by comparison, their Kb will be higher. So higher Kb means stronger weak base. Seems very oxymoronic, but that's what it is. So high Ka, stronger acids, high Kb, stronger bases. Now, because we know that the relationship between Kw, Ka, and Kb is as follows, where Kw is really Ka times Kb, this was discussed in a previous video, it goes to reason then, using sort of mathematical proportional reasoning. If Ka is really high, then Kb is really low. And that kind of makes sense, because if the acid has a very high Ka, it means it wants to give up its hydrogen quite a lot, which means its conjugate base doesn't really want to absorb hydrogens as much, so its Kb is lower. And similarly, if Kb is really high, then Ka is lower, because a high Kb means that the conjugate base wants to absorb hydrogens, and its conjugate acid doesn't really want to give up its hydrogen. So there we go. So that's kind of our relationship and how we can sort of figure out whether a weak acid or a weak base is stronger than another weak acid or weak base. We just look at, is the Ka higher or lower than the other thing we're comparing against? Alright, so here's an example. We're going to list the following in order of increasing acid strength. So we're going to list it starting from, there's I think 5. We're going to list this from the weakest acid to the strongest acid. Okay. Oh, it's only 4, sorry. Okay. So the strongest acid we can see right away is this, H2SO4. This is a strong acid. So that's going to be at the very end of our spectrum. H2SO4. Okay. Now the next one, next strongest, is probably going to be this one, I say probably because it has 3 hydrogens, so it's most likely going to be able to give up one of its hydrogens compared to the H2CO3. But to confirm, we'll look up at our table. So I'll pull up that table real quick. Okay, so here's our data booklet. Scrolling down, there we go. So here's our acid table. We are looking for H3PO4. There it is. It's pretty high up on the weak acid side. H2CO3 I think is down here, so it's H2CO3. So notice H2CO3 is below H3PO4, so H3PO4 is a stronger weak acid than H2CO3, and you can even compare their numbers. Here, the number is 7.5 times 10⁻3. H2CO3 has a Ka of 4.3 times 10⁻7. So H3PO4 would be the next strongest acid, followed by H2CO3, and that leaves then that the HCO3 minus is the weakest of these acids, and it kind of makes sense because it only has 1 hydrogen. It's also got a negative charge, so it's more likely to attract hydrogen ions than it is to give up its last one. And we can even check here, the bicarbonate ion is down here. There's the bicarbonate ion, and it's got a very small Ka of 5.6 times 10⁻11. So if we're asked to sort of determine how strong an acid is, we first determine, is it a strong acid? If it's not a strong acid, we simply compare Ka values. Now, what does this mean? Well, in a lot of cases, this is most interesting when you start mixing together different solutions or different acids, and it becomes quite interesting when you have amphiprotic substances present in the solution. Because if you have amphiprotic substances, these are substances that can act as an acid or a base when in solution. And if you mix them together, one of them has to take the acid form and the other one has to take the base form. And the question now is, which one is the acid and which one is the base? Now you guys can probably figure this out because I just mentioned that stronger acids have a greater ability to give up their hydrogen and weaker acids do not. So when we're looking at this situation here, so here, HCO3 minus, HSO3 minus, we simply ask, which one of these substances is the stronger acid? Is it the HCO3 minus or is it the HSO3 minus? So which has the higher Ka? What this means then is that whichever substance has the higher Ka, that will take the acid form. So this will be the acid. This will be the acid. And it basically forces the other substance to become the base. It's kind of like reverse bullying almost, because rather than taking the hydrogen, the stronger acid will give the hydrogen to the base. Forces the other substance to be a base, right? So just imagine if these two were kids in school, whichever one's the stronger acid will basically say, hey you, take my hydrogen. Let's say, like, actually I'm not sure which one it is. Let's see. I want to say, I think it's HSO3, I think, because HCO3 is really low, as we saw down here. Oh yeah, there's HSO3. HSO3 is up here. It's higher than HCO3, so HSO3 is going to be the stronger acid. So HSO3 basically tells HCO3, here, take my hydrogen. You can't do anything about it. I'm stronger than you. I'm giving you my hydrogen. And it ends up creating this equilibrium. So the HCO3 is forced by the HSO3 to accept a hydrogen to become H2CO3, and then this becomes SO3 2 minus, like that. So because HSO3 is a stronger acid than HCO3, it forces this equilibrium or this reaction to go this way. Now, interestingly enough, once this equilibrium is established, the equilibrium will actually favor one side or will favor one of these sides. So the initial reaction creates the H2CO3 and SO3 2 minus, But then because of chemical equilibrium, one of these sides is going to be more favored than the other side. Okay, so how do we figure that out? Well, we have kind of two reactions to work with. We have a forward reaction where we have the HSO3 giving the hydrogen to the HCO3. And we have a reverse reaction where the H2CO3 is giving the SO3 2- hydrogens to sort of force the reverse reaction. And to determine which side of the reaction is favored, whether it's the reactant side or the product side, we kind of look at, okay, both sides have an acid. So on the reactant side, this is the acid on the reactant side. On the product side, this is the acid on the product side. And now at this point, you can sort of think of it kind of like a tug of war. Okay, which of those two acids is stronger? Stronger acid will force the reaction to go in the other direction. So if HSO3 is stronger than H2CO3, the reaction will go this way. If H2CO3 is stronger than HSO3, the reaction will go this way, or at least it'll favor. Sorry, it'll favor that side. So if HSO3 is the acid or stronger acid, then it'll favor the product side, which means more product will get created. If H2CO3 is the stronger acid, that means then that the reactant side will be favored, and they'll tend to stay in this form over here. Okay, so that's what we're going to try and determine. Okay, so what we can do is we can then write a KEQ equation to sort of help us figure this out. Now here's the KEQ equation written out, and currently it doesn't look like it means much other than this is just how we would normally do any other KEQ equation, right? Now the interesting thing about this is we can actually rewrite this using the Ka of each acid. Okay, and what I mean by that, I'll show it to you guys in a moment, is that both of these equations look very similar to the Ka of their respective acids. All right, so let me just quickly write out the Ka of each acid. So here's the Ka of HSO3-. This would be calculated as follows. The concentration of SO3 2-, it'll create some amount of hydronium, and this will be all over top of HSO3- like that. Okay, and then the Ka of the other acid, so this is the product acid, H2CO3, this Ka would look like this. Its conjugate base, its acid or the hydronium, and then the acid concentration of H2CO3, like so. Okay, so if I look at my KEQ equation here, so looking at this equation, and I look at these two equations here, okay, they look kind of similar, because they all have SO3 2-, H2CO3, HSO3-, and HCO3-. How this equation relates, or how this equation, and these two equations, how they relate is as follows. Okay, if I take the Ka of HSO3- and I divide it by the Ka of H2CO3, I get the following. SO3 2-, H3O+, this is all over HSO3-, all divided by HCO3- H3O+, and then this is H2CO3. All right, cleaning up this gargantuan fraction, I get the following. This HSO3 minus can go to the denominator. This can go up into the numerator. The H3O pluses will cancel each other out, and we get the following. SO3 2 minus times the concentration of H2CO3 all over top of HSO3 minus and H2CO3, which is really just KEQ of the equilibrium that I mentioned before. Some of you are probably wondering, well, that's silly, we just proved that equation. Yes, but more importantly, we came up with this relationship where the KEQ is equivalent to the Ka of my reactant acid, the HSO3 minus, divided by the Ka of the product acid. Now, how does this help us? Well, if you remember from our dynamic equilibrium unit, if KEQ is greater than 1, this means then that the forward reaction is favored. Forward reaction favored. Okay, and if KEQ is less than 1, then the reverse reaction is favored. Okay, if you remember from our dynamic equilibrium unit. Now, rather than actually calculating all of those values for the concentrations, all we need to do is, do I know the Ka of HSO3? Do I know the Ka of H2CO3? If I know those two, then I can calculate my KEQ and I can determine which of the reactions is favored. So I'll write out the equation again. HCO3 minus plus HSO3 minus will form an equilibrium with SO3 2 minus and H2CO3. So if my KEQ is greater than 1, that means my forward reaction will be favored. So the end result will be after mixing this substance and this substance will be more of this. Okay, that's if KEQ is greater than 1. If KEQ is less than 1, then the reverse reaction will be favored. So after mixing this and this, we will basically have more of this stuff than we have this stuff. Okay, and what's even greater about this, so it's even more amusing from a mathematical perspective and kind of helpful, you don't even need to calculate anything to come up with, is KEQ going to be greater than or less than 1? All we really need to know is, okay, if I take the Ka of HSO3, because in order for KEQ to be greater than 1, the Ka of HSO3 minus must be greater than the Ka of H2CO3. That's the only way that this mathematical equation will give me a KEQ greater than 1. And similarly, if KEQ is less than 1, then the Ka of HSO3 minus is less than the Ka of H2CO3. So we don't even need to do any math. We just have to compare, is the Ka of this acid bigger or smaller than the Ka of that acid? And that'll determine whether the forward reaction or reverse reaction is favored. So let's look. Ka of HSO3 minus, if I pull it up, is 1.0 times 10 to the negative 7. 1.0 times 10 to the negative 7. Then we'll look for the Ka of H2CO3. The Ka of this, H2CO3 is up here, 4.3 times 10 to the negative 7. 4.3 times 10 to the negative 7. So which number is bigger? This number is bigger, so reverse reaction will be favored. Reverse reaction is favored. That looks like an O. Should be a U. There we go. So basically this means then, if I take this substance and I mix it with this substance, it'll form this and this, but because the reverse reaction is favored, not much of this, so very little. Very little product is made. Okay, very little product is made. So it could sort of be like, okay, HSF3 forces the HCO3 to get its hydrogens to become H2CO3, but it's not very strong, and the H2CO3, once it gets created, is basically like, nope, I'm good, you can have your H back, and then just forces the reaction to stay on this side of the equilibrium. Okay, it's not to say that the reaction doesn't actually go forward. It goes forward, just doesn't go forward very much, because the H2CO3 is a stronger acid, so forces the reaction to go backwards. But because HSO3 is stronger than HCO3, some of the HSO3 is able to give the HCO3 a hydrogen to force or to cause the reaction to go forward. So the end result kind of here is that if you are given two amphiprotic substances and you are asked to determine which is the acid and which is the base, all you really need to do is determine which Ka is bigger. So the KEQ of that amphiprotic equilibrium really boils down to the Ka of your reactant acid. So the reactant acid is the acid that is on the reactant side. And the Ka of the product acid, which is the acid on the product side, and it's determined, okay, if KEQ is less than 1, favors the reverse reaction. So this would be Ka of the reactant acid is less than the Ka of the product acid. And in this case, this would be the Ka of the reactant acid is greater than the Ka of the product acid. Okay, there you go. So now you can compare which acid is stronger and which acid is weaker, simply by knowing the Ka of a particular of each substance. Okay. Now there are some interesting things with these with the weak acid equilibria, is that if a substance has no hydrogens, then it obviously can't be the acid, so it has to be the base. And you can sort of see that here, in that on this side, the SO3 2- has no hydrogen, so it's kind of has to be the base. There will be some cases where you'll have hydrogens on all substances in the equilibrium, so you'll have to compare the Kas or just watch the reaction and see which one is giving up a hydrogen, which one is losing a hydrogen, or gaining a hydrogen, sorry. Alright, so here's an example. I think there are 3 examples here I want to illustrate. Okay, so we're going to mix several different substances, and we're going to determine kind of which is the which side of this equilibrium is favored. Okay. All right, so let's start with this first one. So we have HS- plus HCO3-, and this is going to form an equilibrium. So the first step is to determine which one is going to be the acid, which one is going to be the base. I'm going to guess it's the HS-, because HCO3- is pretty weak, but I want to confirm that. Oh, maybe I'm wrong. HS- isn't even on the chart. So there's HS-. So HS- is really weak because it doesn't even show up. So we'll just say HCO3 is my acid. So this is my acid. That'll allow us to write the following. HCO3- gives its a hydrogen to the HS-, so force it to become H2s, and then it becomes CO3 2-. All right. The H2s has to be the acid because the CO3 2- cannot give up a hydrogen because it has no hydrogens to give. So here are my 2 acids. This is my reactant acid. This is my product acid. Now we determine which Ka is bigger. Ka of HCO3-, Ka of H2s. Let's look. I think we know the answer because I already saw it. There's H2s. It's 9.1 times 10⁻⁸. HCO3- is 5.6 times 10⁻11. So HCO3- has a lower Ka than H2s. So in this reaction, reactant side favored. And if the reactant side is favored, that means that the reverse reaction is also favored. So reactant side favored, or another way to think about it is reverse reaction favored. Reverse reaction favored. All right, let's try the next one. Maybe you can try the next one. You can pause the video, try the next one, and then I'll go over it after you've tried it. Or not, it's up to you. You really should try it on your own first, because I did the first one for you. So you can pause, try it out, and then see if you're right. Alright, so here we go. We have our acid here. We are going to form... I actually don't know which one. HSO3 is pretty weak, I think. There's HSO3. H2CO4 is... Oh, it's way up here. Okay, so H2CO4 is stronger. So this will force the HSO3 to become H2SO3, and H2CO4 becomes C2O4 2-. So this is my acid. This is my acid. Okay. Which one is stronger? Let's look. There's H2CO4-, and we are looking for H2SO3. H2SO3 is way up here. So H2SO3 is the stronger acid. So Ka of HC2O4 is smaller than the Ka of H2SO3. So again, reverse reaction favored. I can't spell today. Right, reverse reaction favored. Or another way to think about it is that the reactant side is favored. Alright, last one then. Again, if you want to try this out, pause the video, try it out yourself, and then we'll see if you are correct. Alright, so HCO3 and HPO4-. HCO3-, HPO4 2- will create an equilibrium with. So which one is stronger? HCO3 is pretty weak. It's way down here. HPO4 is also pretty weak, which is down here. It looks like the HCO3- will forcibly give the HPO4 its hydrogen to become CO3 2-. So this is my acid, and on the other side this is my acid. So now we compare. Ka of HCO3-, how does that compare to the Ka of H2PO4-? Let's look. H2PO4 is here. HCO3 is here. So again, this is going to be again reverse reaction favored. Reverse reaction favored. Will it always be the reverse reaction favored? No, not always. It comes down to you guys need to check the resulting acid and resulting acids on the reactant side and the acid on the base side, or not base side, product side, and then see which one is actually bigger. Just so happens all of these examples that the reverse reaction is favored in all of these examples. But again, not always the case. You have to check. And again, to recap, it really just comes down to, is the Ka of the reactant acid, or is it bigger? Yeah, is it smaller or bigger than the Ka of the product acid? There we go. Okay, that's how you can tell which acid is going to be stronger. Just simply compare Ka values. Because remember, Ka is an equilibrium, and it tells you kind of how much the forward reaction is favored or how much the reverse reaction is favored. There we go. Alright, so your assignment then, if you have your textbooks with you, will be as follows. If you guys haven't done the quizzes yet, I highly suggest you do them. They're really just meant for practice, so if you're not getting them right, probably should contact me. And you guys all know how to contact me.